after working 3 years on the SELFY project is that we aim to have impact. And this impact basically is that we are sure that these results will contribute to building a secure, resilient, and trustworthy CCAM. How? We will see how we are calculating this, but indeed, a system like SELFY, which allows for a cybersecure and resilient system, is probably going to reduce quite a lot the accidents, also the disruptions in the mobility systems. At the same time, we also aim to increase the trust because we need the adoption by the society of the CCAM systems. And of course, as we are working here with European entities, basically, we also want to foster the new job positions. We want to be and to have European systems and solutions to be shared with the industry. Here are a list, just examples of KPIs that we are following in order to make sure that we make this impact. As you can see, for instance, these are rather technical, but at the end, they are building the robustness of the full system. As you can see here, we are going to increase onboard field of view. We are going to identify as many vulnerable vehicles and security breaches, of course. We are also aiming at reducing the detection time and putting in place countermeasures in a very fast time. We are going to enter a bit more on details with this, etc. We have quite a lot of KPIs. Some are also related to the trustworthy and secure communications. Others are related to the secure software of the over-the-air, And finally, anonymization is also a key point here, and you will see some examples. So last, before we enter into the detail on each of the tools, this would be the unique selling points of the SELFY results that we are happy to show here. First of all, we are pretty sure that having a layer, a security layer such as SELFY is going to minimize the frequency and the severity of incidents, which is translated by a reduction of operational and liability costs. Also aiming at a faster time to market for security products. Why? Because we are building a system which is interoperable, easy to integrate, and also agnostic to any trademark. This is important because this means that it will be easily replicable to any ecosystem, any OEM, and so. This for sure will enhance the brand trust because, as you've seen, I'm repeating trust quite a lot because it's really one of the main pillars of this project. We are also working on data-driven decision-making, risk management, and finally, SELFY is quite modular. I talked about a toolbox, 3 macro tools, 21 tools in total, which are completely modular, that they can be used all at the same time, or just using some modules that could be, for instance, licensed or integrated into different service offerings. So until here we have the overview of the project, but I'm really happy to welcome here Christoph Pilz from Virtual Vehicle, who is the one in charge of one of these 3 macro tools. The first one, the situational awareness and cooperative perception. Welcome, Christoph. You see that it's not very easy.
Thank you, Fanny. Thank you for introducing me. So my name is Christoph Pilz, and I am more or less involved with the team that is doing the basic layer for SELFY for the eyes of the project. Yeah, so I structured it in 3 parts only to give you an overview of the challenges we have and then how we approached it and what are the highlights, a few highlights of what we did. For the challenges, the part of us is called situational awareness and collective perception, and I want to walk you through the situational awareness. What is it and what are the challenges here? So if you follow the below part of this slide, then you can see and you can imagine yourself an intersection with lots of vehicles and some infrastructure. All of them have camera, LiDAR, and radar sensors. And with this, you perceive your environment. You do this from vehicle perspective and you do this from infrastructure perspective. And what we want to have in the beginning is just nuclear situational awareness. We want to know where everyone is and what they are doing currently. The challenges are here by the multitude of sensors we have and the dynamic environments. And for processing, we can here already have an evaluation for cyber attacks and for system faults. What we want to do here is we want to compare the sensor data, we want to compare all the input data and find out if somebody is attacking our system or if there is a fault. And in the end, everything should be time critical. Of course, if you have an automated vehicle and you get the data 10 to 60 seconds later, that's not of much use. The second part of us is the cooperative perception. So I talked before that we detect everything and now we are processing everything and putting everything together. The idea is to have data fusion. I don't know if you can see it the right way, but on the left picture, you see an ego vehicle that is marked on a green lane. And the ego vehicle sees some other vehicles, some other objects. And it gets information from V2X, so from other vehicles, from other infrastructure, and then fuses the data, and we have just simply said one bounding box, one vehicle that we think the vehicle is. And what we can do here is we can compare this input sensor data and we can check it for sensor faults and for attacks. The impact is that we now know our some environments, we can increase our field of view, and we can be the input source for later work like the VSOC. So how did we approach that? You can see this slide like a table. We have the left part and the right part as two columns. We have the concepts and the domains. For the concepts, we have just three. We have the perception, the communication, and the fusion. For the perception, we have everything related to just getting the sensor data at first. We have the cameras, the LiDARs, the radars. We have all of the local processing in the car to get out the objects. Then we take those objects from the vehicles or from the infrastructure, put it in specific formats, and send it to everyone else. Again, with low delay, else we cannot use it. And finally, when we receive the data somewhere else, we fuse everything together and we try to have one view of our environment, one situational awareness. And we do this in two domains. We do this in the vehicle and we do it in infrastructure. Both have a little bit different challenges. The vehicle is moving, doesn't need probably a few informations on the details of the object, just that it is there. The infrastructure probably needs a little bit more information of the objects themselves, but it's not that time critical, for example. Those are different domains. Those we have to check differently. We have a few modules that came out of it. I list them afterwards for you, but I just want to step through 4 of them for you to show you how it looks like and how we can split it up. The first one is the sensor fusion and anomaly detection. What we are doing here, if you follow me through the debug view, you can see on the screen. You can see here on the right the LiDAR and the camera sensors highlighted. And the camera and the LiDAR, they detect one vehicle, for example, or they detect one pedestrian. What we can do now here, only with 2 different sensors, we can already check if there is some malfunction, if everything is overlapping, and yeah, we can already detect if some additional V2X data is sent to us where we detect, okay, there is an attack on the system. This is more or less completely simplified how this works. A second module I want to explain to you is the situational assessment module. And what you can see here on the screen is the ego vehicle that is driving along the road and it is jerking from left to right. This could be real vehicle jerking. It could also be just V2X spoofing. The important thing is we can detect it. In a few seconds, we will have another example. The lateral case, where we simulate that the vehicle is not staying in lane. So what you see right now is that the vehicle is driving straight ahead, and now it is switching to the other lane, but not really, and we can detect this anomaly with our system and react on it. This is the basic and lower case that we need for inputs of later stages. A third module is the vehicle situational awareness tool. This is more or less what the vehicle itself sees, what the vehicle can provide. On the right side, you can see the camera overlay of an automated vehicle, and you can see labeled objects, in this case, the cars that are visible. And this is the data we collect in a local dynamic map, so the map of the vehicle that can share this data then via V2X. When we share this data, we come to the data aggregation and fusion part, and there we have the other side. Previously, with the VSAT, we shared the data, now we collect it. And I want to walk you a little bit more slowly through this one. In the center of the picture, you can see faintly highlighted a gray vehicle. This is the ego vehicle. And the ego vehicle detects other objects with blue bounding boxes. Right beside the gray vehicle is another vehicle. It is faintly visible that this is a orange bounding box, which is the cooperative awareness message it is sending out itself. And the other vehicle sends us green bounding boxes from their perception. When we start the video, you can see how the data is coming in, the local perception and the other perception. This is just the raw data before the fusion, before any post-processing we are doing. And this is how we can extend our field of view. In this case, the vehicles are standing aside each other. If they would stand around the corner of a building, then you have a real good extension of the field of view. As I said, these are just 4 modules of what we did. If you visit us tomorrow or the next 3 days on the booth, we can explain to you all the other tools we have. You're welcome. My colleagues can get in a lot more detail of what we have done. In conclusion, to round it up, the situational awareness and collective perception toolbox is the eyes and ears of the whole project. We provide the data, and just to highlight a few KPIs for you so that you can imagine what we are doing, we increase the field of view by 100%, for example. When you imagine that you have 2 vehicles split by a house in the middle, the field of views do not overlap from the vehicles, then you have an extension of 100%. We increase the detection rate not only from objects, but also from threats. And yeah, we can improve the CCAM reliability overall by just having more data. Thank you.
Thank you. Don't go. Just in case we have some questions in the audience. Are there some questions? Are there some questions online? Indeed, I have a question for you.
Yes.
I would like to know what part of the job in your case, in this macro tool, was the most challenging one, to your opinion?
Mm-hmm. So the most challenging part was bringing everything together. It is really difficult, as you have seen, that a vehicle or infrastructure is detecting stuff. You have to bring it together at some point, and all the partner input has different interfaces, and bringing everything together is a real big challenge for such a big and small project.
A question there.
I can use the mic, it's better.
Yeah.
So I'm Andreas Rehner, THI. I've seen there's some colleagues from us also in the project and attending this meeting. From my understanding, the situation awareness is just the perception of the ego vehicle, or what the ego vehicle sees. The collective perception is the fused data from environment, infrastructure, plus vehicles. Is this correct?
More or less. So the situational awareness is on a nuclear level for each. If you take one actor, one ITS station, one intelligent transport station, this is the situational awareness one can have, and the collective perception is on top of it, granting everyone more situational awareness even.
So you can use the collective perception to validate situational awareness on the local unit?
Yes, you can do that too, yeah. Yeah. If you have one vehicle that is doing something and 5 vehicles around it, then you can validate with this, yeah.
Good. Many thanks again, Christoph.
Thank you.
I just discovered that you were driven by the 80 series Knight Rider and that you aim to teach vehicles to talk. So future is quite close right now. Thank you again.
Christoph, before you leave, there is a question online.
Sorry.
I will read it out, okay? From Lisa, that she says, is your toolbox openly available, and if yes, where?
I'm not sure if everything is openly available, but our deliverables are completely public. That's what I know. I know that especially the WIF part, so the part from virtual vehicle, is publicly available. And I know that major parts are available. We should go into specifics of what you exactly want to have from us. But this is, to wrap it up, probably your question, what we did is we tried to, in the deliverables, put everything as public as possible so that you can grab it and do something with it. So, yeah, I don't know if I can answer your question with this.
I think it's fine.
That's fine?
Yeah, sure. Thank you very much again, Christoph. Okay, so let's go to the next macro tool, which is going to be presented by Victor Jimenez. Victor Jimenez is an IT/OT researcher at EUCAD too, an electronics engineer, and he's the technical coordinator of the SELFY project. So come on, please, and explain us the cooperative resilience and healing system. Thank you.
Thank you, Fanny. So, hi everybody, thank you for joining this event. I'm lucky to be the technical coordinator together with Fanny, and I am also the work package for leader, which is related to the cooperative resilience and healing system. Yeah? Okay, I see the problems that you had. Yeah, following the order that Christoph was also using, let's talk a bit about challenges and objectives that we have in the CCAM environment related to resilience. Then we will see the architecture and the set of tools that we have developed in this work package in order to cover these challenges. Afterwards, we will see some main results and latest, some conclusions. Yeah, so related to objectives, our work package work, it's about resilience, okay? So we want to provide tools, hardware tools, software tools, algorithms, intelligence to the system in order to run this kind of self-protect, self-healing, self-defense actions. Okay, that's why the name of SELFY, it's self-try to protect. And it is related also to providing this intelligence to the system to increase these levels of autonomy. At the end, also, like the other tools in SELFY, we want to provide this collaborative mechanism in order to improve resilience and also situational awareness, like Christoph was commenting, and trust and data management system that we will comment Adrian later about. But everything is connected, and at the end, in our case, we want to provide this resilience to the system. And another important point is that we want to provide these tools for the OEMs in order to manage the cybersecurity incidents, cybersecurity problems, privacy, to their car fleets. So, again, this is related to the challenges. If we want the CCAM, the automated vehicles on the roads, that they are working safely and with security and with privacy. So we have to increase this robustness and detection and mitigation rate in case of attacks or leakage information and so on. And today there are a lot of tools based on AI, not only for detection, but the attackers, they are going to use this kind of tools. So it's also a challenge to try to use artificial intelligence to try to detect different kinds of anomalies, new attacks, and try to respond to these attacks. Again, the challenge is to provide this intelligence to a system and try to respond to a threat in a brief period of time and triggering reconfigurations to the system in order to reach a safe status. Of course, another point is to reduce human interventions. So the more everything is connected and automated, we are going to reduce this problem, these human errors that in all the sectors they happen. Also here they can happen. And we try to identify injected faults in the system and at the end, improving security, safety, reliability, privacy. I mean, many adjectives could be put here. So what we did, once we defined these challenges and these objectives and we got the requirements and so on, we defined an architecture for the cooperative resilience and healing system, which is composed by 7 tools. The tools, they are deployed at cloud level, infrastructure level, and vehicle level. And they are, okay, let's begin with the cloud level. At this point, the VSOC, and why? Okay, VSOC is more or less, we can say, it's kind of a brain of SELFY project. It's collecting all the events, is detecting all the things that they are happening. Many tools have interfaces with the VSOC, providing this kind of information. The VSOC has some intelligence there, and they can provide also responses in case of these incidents, anomalies detected, and so on. It can trigger a secure software update. It can trigger an audit action, all these things, okay? So it's kind of, and it also provides panels, dashboards to the users, okay? It's an important tool. All the tools are important. Together with the VSOC, there is the interaction-based verification and validation tool. This tool is checking all the interactions of the systems. These interactions, they are in some kind of sequence that the tool knows in advance. And if there is some deviation from the planned execution, it raises an alarm and sends to the VSOC this alarm. So there is kind of anomaly, could be an attack. On the right side, on the infrastructure, on the right side unit, we have the audit box. Okay, the audit box is a kind of box installed in a right side unit, and its main function is try to audit interfaces or attack vectors in the vehicle, like the Wi-Fi vector, Bluetooth vector, and try to, in case there is some kind of anomaly detected, the VSOC can trigger an action to this audit box to audit, to see if there is a vulnerability, maybe an open port, something like this. And it can also detect jamming situations. That is near this roadside unit. Imagine there are many roadside units over all the city. If there is someone that is playing with a jammer and is provoking jamming on the Wi-Fi vector, on the GNSS vector, or spoofing a GNSS position, it could be detected and informed to the VSOC. Something is happening here, okay? And the VSOC will make the actions that they think. Other tools, on the vehicle level, we have the situational assessment module. This tool is belonging to Work Package 3 because it's related to situational awareness. But also it's linked to the Work Package 4 because it's detecting this kind of anomalies at vehicle level. It uses the information of the environment, as Christoph was commenting, but also the CAN messages, the planned trajectory of the vehicle, and in case there is some anomaly detected, it assigns a risk level to this anomaly, which can be used by other tools. In that case, also it's used by the safety operational tool, which is another, I think, really important tool in the SELFY project because it provides a safe reaction to the vehicle in case there is some kind of attack. For instance, it could be a GNSS attack, or the GNSS is malfunctioning, and it can make a maneuver and bring the vehicle into a safe state. So that kind of tool is important also, assuming that in case there is an incident with the vehicle, we can trust the system that brings the vehicle into a safe state, which is really important, the safety. Whatever. We have also the robustification tool, which is a set of algorithms that they are provided in an adversarial environment in cooperative driving. You will see there is some use cases related to this, and it provides also resilience to these controllers used in these situations. And some examples, it can be resilient to a jamming attack, also denial of service attacks in this kind of, for example, the platoons, the platooning. And last but not least, we have also the artificial immune system, which is a tool that also it's able to detect anomalies in the communications of a vehicle, and it can also learn from these deviations, learn about the solutions, and it can somehow try to self-heal the system in case that there is a problem. It's also a collaborative tool. So this is the architecture and the tools. Okay, so the main results are related to the tools. We don't have a lot of time, but one of the cases that is really interesting is a use case, which is the robust platooning, in which there are 4 tools of the work package: robust, the safety operational tool, the VSOC, and the verification and validation tool. So in that case, you will see now a video, and you will see how there is some kind of situation, maybe an attack that is attacking the intermediate vehicle of the platoon, and it loses their localization capabilities. Thanks to these tools that they are coordinating, as I was commenting, the anomaly detection, providing information to the VSOC, assigning a risk situation to this situation, you will see, like in that case, the vehicle in the middle of the platoon will evacuate the platoon, and the rest of vehicles, they are going to join and continue with the cooperative driving. So let's see a video. It's 2 minutes. Let's see, if it's so long, maybe we can forward it. But you see here there are 3 vehicles. The first on the link side, there is the first vehicle, the second on the right at the top, and the third one is the right at the bottom. At this moment they are moving, and in the middle you see this the LiDARs, what they are seeing, all the vehicles. Okay, at some moment, okay, they are driving, they are going to pass near other vehicles at some moment, but it will take some, yeah. I can swear you it will be 1 minute only. So they will see the vehicles. And you will see like the vehicle in the middle, which is the one affected by the attack. It will leave the platoon, and the first vehicle and the third vehicle, they will regroup the platoon, so providing, let's say, a safe reaction. Now you see the vehicles that they are perceived by the platoon. And at some moment, yeah, you see now the second vehicle is leaving the platoon, and then the first and the third vehicle, they are regrouping, and they are forming the platoon again. So this is a nice case that is being done by these 4 partners. There are 4 tools here collaborating, and it's a simulation use case. Another one that I will skip the simulation, the video, because it was already shown by Christoph, is another use case in simulation, that there are the situation assessment tool and the safety operational tool, which is the one that you have seen already, that in that case, the second vehicle of the platoon detects some anomaly because the vehicle, the lateral controller is making some strange behavior, maybe due to a cyber attack. And the tools detect this movement, and then the safety operational tool, it reacts according to the risk information provided by the situational assessment tool. So I will skip the video because maybe also I am at minute 11, so we don't have a lot of time. Okay. Yeah, other tools that we have, here what you see, it's a digital tool, so I didn't put a video, but this is the screen of the audit box. As I commented, what you see here is on the left-hand side, there is the database, the internal database of the audit box, and the VSOC can send a VIN number to the audit box. In case that this vehicle approaches this roadside unit, it will be audited by the audit box. On the right side, you see all the vehicles or the networks that they are passing near the audit box, and in case that it matches the one which is stored in the database, it will be audited, that vehicle. This is another screen. You see here how in the VSOC is collected, but afterwards in another slides of another colleague, you will see more details about the VSOC. And yeah, this is another functionality of the audit box, what you see here, which is the jamming detection. You see here we have a jammer, and you see the signal of the Wi-Fi, this peak you see on the right top part of the slide. This is a small peak, which is a Wi-Fi signal. And I can tell you there are more peaks, but they are now, because of the jammer, they are hindered, okay? So the audit box also can detect Wi-Fi jamming attack, and also, not shown here, but also GNSS jamming or spoofing attack. And the last tool is the artificial immune system, which has a video. I put here a video. There is some sound. Thank you. So this tool, as I was commenting, you see here the text, so you can read it, but it is using some algorithm which is called the negative selection algorithm, which is an artificial immune system algorithm, is the one used here, and it detects deviation or anomalies in the communications. Okay, it's also a digital tool. Maybe we will leave 30 seconds and I will skip the video, but you will see now a lot of screens of the validation done in the lab now. And you see on the left top side, there is the BSOC, and on the right top side, there is the right side unit. And here at the bottom, the two windows at the bottom at the right, there are some attacks that they are triggered. And then that we see on this video that you can see on YouTube. Don't worry, I will skip it, but you can see on YouTube. The artificial immune system is detecting such kind of anomalies and informing the BSOC about them. So these are the tools of the cooperative resilience and healing system. And at the end, the conclusion is that we are providing these tools, which are orchestrated by the BSOC, that provide this resilience to the system and these self-abilities to the system that to self-detect, self-protect, and self-respond, which at the end provides more levels of autonomy. We are contributing also to some KPIs, important KPIs, which has been listed before, like increasing the robustness level, detection rate, mitigation rate, identification of vehicles vulnerable to an attack, and also triggering countermeasures in a brief period of time, okay? And identification of vehicles and security breaches. At the end, it goes about resilience. Yeah, and that's all. So thank you very much for your attention. If you have some question, Fanny, or people here.
Questions in the room to Victor? Are there questions online, maybe?
No, for now, no. None.
Okay, no question, Victor. Maybe one from my side, okay?
Yeah, for sure.
What would we miss if we would like to already upscale these the healing and protection systems? What do you think is missing still? What could be a next step after the SELFY project?
Yeah, I think our use cases, even some tools they have tested with some upscaling. I know, like for instance, the BSOC has tested with many, the load balancing. I see that there are many requests. But these tools, they are done in let's say, in an environment with few cars and few units, few elements, few roadside units, and so on. And when we are speaking about upscaling or put it in the real deployment, for sure all the systems, they are going to have much more interactions, much more traffic. So at the end, this is something that it should be tested. These kind of situations with a lot of traffic, a lot of incidents, a lot of elements communicating. This is one of the important things that they should be covered.
Okay, thank you, Victor. So we
still
have quite a lot of work after SELFY.
Thank you.
Okay. Let's go to the third and last macro tool, which is going to be presented by Adrien Jousse, who is a cybersecurity researcher at CEA. He's working on different topics, such as the digital product passport, trusted platform modules, remote attestation, post-quantum algorithms, and so on. So can you please explain us the third macro tool? Sorry.
Yes, I can. I will try.
You understood me.
Yeah. So I will now speak about the Trust and Data Management System macro tool. I will follow basically the same outline as my colleagues, starting with the objectives that we had in the Trust and Data Management System. So, as the name suggests, Trust and Data Management System is mostly about trust and data management, obviously. But there is also cybersecurity and anonymity. So we wanted to preserve the integrity of the messages that are exchanged in the CCAM, because CCAM is about exchanging data between all the different agents that can be working together. But sharing data doesn't mean that we have to compromise on anonymity. So this is also one of the second objective that we had. We also wanted to preserve the usability of data, because when you anonymize data, sometimes you can lose a bit of, the data is less good, and we didn't want to have that. We also wanted to improve explainability, so why something is not working at a given moment, for instance, and how can we fix it. And also explore the use of post-consumer algorithm, because as you all know, car and road infrastructures are living a long time, and they have to be able to survive the foreseen post-consumer threat with the arrival of the consumer computer. How are these objectives challenging? Well, they are challenging because we have to ensure that legitimate users can exchange data securely in the CCAM environment. There are also, another challenge is also to integrate new cryptographic algorithms that are not really known, that we didn't use them for 10 years, let's say, and we have to see if they can fit within the automotive constraints. So that is to say, can they fit in memory, and do they have latency that are compatible with the requirements of the automotive domains. Also, we want to share data without giving up on anonymity, so that CCAM can work properly. We want to reduce the need for human intervention, so that you don't have to go to the car dealer when a software in your car is broken, and also to detect malfunction of the system. How can we do all that? Well, to do that, we design different tools that are organized in the following architecture. So this is a really high-level functional architecture. I will be rather quick on it because I will go into more details for each of the tools in the last part. But on the left side, you've got privacy-focused tools. And then on the center and right part, you've got tools that are doing trust, cybersecurity, update, etc. As you can see, basically anyone can communicate with anyone because security can be provided to any tool. We also can update the tools. We want to be able to attest them and to provide them with post-consumer algorithm. To describe a bit more what is done in each of the tools, I will first start with, the results tool by tool, starting with the data anonymization tool. So this is a tool that is anonymizing a field of view. Here you can see a car that is driving through a parking lot, and on the field of view you can see that the license plate and the face of the pedestrian are blurred. And this is done in the vehicle in real time while it is driving through the parking lot, so that the images that are captured by the camera can be shared without compromising the anonymity of the pedestrians that are encountered or of the cars that are also seen in the parking. Another tool that is also focused on privacy is, as the name suggests, the privacy utility tool. This is an algorithmic tool that is designed to add noise to data while not compromising the usability of data. A way of anonymizing is to add something else to the original data so that the data of interest is mixed into something else. Here on the left, you can see in the original scheme, so without that tool, that a user is sending data through a public network, such as the CCAM network, for instance, to an algorithm. And someone that is eavesdropping on this network can get that exact data. On the right side, with the immersion-based scheme, so using the privacy utility tool, we can see that the user is encoding the data before sharing it so that an eavesdropper cannot get something that is directly usable. And then a specifically designed algorithm can still use that data without a loss of precision. To give you an idea, on the bottom, you've got the image of the number 3. Before encoding it, we can all clearly see that that's a 3. And after the encoding, we cannot distinguish it anymore in the image. But an algorithm still can use that image and extract information from it. Another tool to design to work with privacy is the V2X privacy tool. So in the V2X standards, it is allowed to change the pseudonym that is used to describe a vehicle. This is even recommended to protect privacy. As you can see here on the capture, we've got a tool that has a V2X identity ABC, if I can point it here. And it is currently assigned a cooperative perception message ID 54. However, when we are sharing CPM messages, we also have to take into account the change of pseudonym in the V2X messages, because otherwise the V2X ID will change and the CPM one will not. So here, when we receive a new V2X message, we can see that the pseudonym has changed to XYZ, and the CPM ID is also updated from 54 to 131, so that in the CPM messages, we will still protect the privacy of the V2X agent. So these were the privacy-focused tool. Now, if we switch to the trust and then security tool, we have the website trust tool. I didn't put a video on this one because it is a tool that is also a command line interface tool, so not really nice to see, let's say, but still really very useful. And this one is kind of the counterpart of the V2X privacy tool. The V2X privacy tool is here to make sure that we can change our V2X identity and forward it in the CPM messages. And the website trust tool is here to make sure that we don't change it too often. Because if it's changed too often, then it can be an attack. So what the website trust tool does is it gets the ID of the V2X agent. And if the same agent is changing too frequently its identity, it's going to decrease the trust score associated with the agent, so that further messages can, for instance, not be taken into account, and thus avoiding specific attacks. On the security side, we have the post-quantum cryptography tool. So this was a tool designed to explore the use of post-quantum algorithm in the automotive context. These algorithms are fairly new, and we still don't know how are they going to perform in some specific scenarios. So the goal was to do a performance assessment of these algorithms. On the left side, you've got the results of one of the performance tests that we did. Others are available in the deliverables on SELFY website. And on the top of the chart, you can see here that we have ECDSA and RSA that are conventional, well-known cryptographic algorithms, and all the others below are post-quantum algorithms. You can see that clearly some post-quantum algorithms are performing really well compared to the conventional ones, and all these algorithms have, as far as we know, the same level of security. However, it is to be noted that for ECDSA and RSA, there are no hardware acceleration involved in this performance test. So conventional algorithm can benefit heavily for hardware acceleration, but as hardware acceleration is not yet available widely for post-quantum algorithm, we thought it was more appropriate to have an idea of the performance only in software. And on the right side, we have a network capture of a TLS 1.3 connection establishment, where we can maybe see, yes, it should be okay here, that the key encapsulation mechanism used, so the line that is highlighted, is Kyber 768, so also a post-quantum algorithm. Still on the security side, security and explainability, we have the remote attestation system. So this tool is designed to see if a program was executed correctly. So on the vehicle side, we've got a program that is currently running, and we want to see if the execution is correct. The first step is for the VSOC to request an attestation to a part of the remote attestation system that is in the cloud, the verifier. The verifier is going to receive this request and request evidence of the execution to the prover that is in the vehicle where we want to attest said program. The prover is going to collect evidence, which in our case is a list of system calls that are exchanged between the user space and the kernel space as the program is running. This list is then sent back to the verifier, which is going to compare it to a reference value which was computed before the deployment of the program. So this way we can eliminate any interaction from the outside when the program is in the vehicle. Then the attestation result is sent to the VSOC. I'm not going to play the rest of the video because it is rather long, but you can see it on YouTube. The results of the comparison is sent to the VSOC, which can then decide to take some actions if the result is not appropriate. So for instance, it can update the desired program to make sure that only a correct version is running. To exchange all of these data, so between the RAS, between other tools, etc., we have to use cryptographic material, and this can be a tricky part to manage. To try to simplify it, we developed the key exchange and management system, and that's a tool that's going to manage the cryptographic materials for other tools. It can work in two scenarios, client to client, kind of one-to-one, and client server, so one-to-many. If one client wants to encrypt data and send the same data to different participants, it can use the server to request a key, etc. I will try to speed up a little bit on this one. And the last tool that we have is the secured over-the-air software update tool, so the SOTA. As I mentioned, the VSOC can request a program to be updated if some malfunctions are detected or if vulnerability is discovered. And this is the tool that is going to do it. So first, the VSOC is requesting the update to be performed. And I don't know if the video is playing. Yes, it is. Once the SOTA receives the request, it's first going to check the signature or the images it has for the desired software to make sure that these are the good images. It's then going to push the update to the desired client, which is going to perform the update and then send back an attestation result to the VSOC. In turn, the VSOC can decide to maybe perform another attestation to make sure that the update went smoothly, or take other measures if something went wrong. For the signature verification, the SOTA did also use a post-quantum algorithm to make sure that the images are perfectly good today and also in the years to come. So, to conclude quickly, the TDMS is a toolbox, as you guessed, that is built on security, trust, and anonymity. It contributes to different KPIs in the CCAM. So, adding post-quantum algorithm, we did show like Falcon and Dilithium for the signature part, but there is also Kyber for the key exchange part, and there are also others. We also worked on the number of injected faults that we can catch using, for instance, the remote attestation system. And this is also contributing to the reduction of human errors and needs of intervening thanks to the SOTA and the remote attestation system. Thank you all for your attention, and I'll be glad to answer some questions if you had.
Any question? Yes?
Thank you, Fanny. Thank you, Adrien. With the V2X deployment and hopefully a boom around the corner, how do you estimate the state of the readiness of the tools, especially for the data anonymization and the privacy?
Yeah, you mean for the V2X privacy tool, for instance, and also the data anonymization? Well, for the data anonymization, as it is directly inside the vehicle, I'd say that it should be fairly okay. I didn't work myself on this tool, but as everything is happening on board, of course, we should have to check if other let's say, viewing environment would be nicely handled. As for the V2X part, it is sitting on the ITS station, if I remember correctly. So I think it will fairly depend on the, let's say, first quality of the antennas and the software stack that sits between the antennas and the part that it's going to really handle the different messages to make sure that it can have enough throughput to handle, let's say, dozens, if not more, hundreds of messages per minutes/seconds.
Okay, any other question? Yes?
Thank you. So I have a question related to the, I don't know how it was exactly called, the anonymization toolbox. I call it this way, hopefully you know what I mean. So this was the one that whatever blurs the faces of people and also license plates. Maybe not required. I'm just I have a question about.
Please go ahead.
The usability of this tool, because I think, and this is my main question, it can be used not only in this specific setting. So it's like you use a regular webcam or any camera, and you just put this toolbox in the stream, more or less, right?
Mm-hmm.
Because so what problem I have is in bicycle research, for example. So we use eye trackers on a bike and have the same problem, basically. Bicyclists drive along during a street or something, recording gaze behavior, for example, and we always have faces, license plates, and things like that in the camera stream. So could this toolbox be used for this kind of research?
I guess so. I think as it is mostly, well, it was specifically trained for the vehicle use case to make sure that it's going to handle properly the data that is seen by a camera inside the vehicle. So we should see if the difference between a camera in a car and in a bicycle use case can be, well, can have an impact on the recognition of the algorithm. But other than that, if the hardware can handle it, of course, should be fairly straightforward.
Okay, so maybe we can later talk offline. Thank you.
Another question?
Hello, Gregor Papa, JSI. I have a top-on question regarding this blurring of identity. Just to clarify, maybe I overheard. So where is the blurring taking place? Is it inside the camera or after the camera? Is it software-based? Is it hardware-based?
So I will let someone correct me if I'm wrong, because I will not be 100% sure on that. It is software-based, for sure, and it is, I think, outside the camera. Yeah.
Okay, is there any potential for the, let's say, vulnerability of this anonymization? So between the camera itself and the let's say, blurring unit, software-based, so that the data leaks, non-anonymized.
It is done before it reaches the onboard unit, the communication unit. So in that sense, it's not exposed to the. It's on the side of the ECU, yes. If somebody would hack directly the car, I guess there is also that vulnerability, but it was not treated in this project, right?
Okay. Okay.
Yeah. So,
good enough.
So yeah, these
just
different segments. I don't think that. Of course.
Yeah, because there are different systems. Some systems even allow you to anonymize, to process data in the camera
In the
hardware
camera.
based on the detection chip itself, to say so.
Yes.
Or very, very close to it. But as long
This
as you said,
solution is
as it
based on deep learning, so we are using actually the detection of the pedestrians and detection of vehicles and license plates, and then doing post-processing in terms of blurring. So it's directly done, it's done in the ECU.
Okay, thank you.
Thank you very much. And I think we have a last question, Adrien.
There is
From
one
online.
question online. Okay. Actually, there are two coming from the same attendee, Dominique Bayel. And he's saying, did you do any performance tests on the post-quantum cryptography tool, especially signatures in the CCAM context? And then he adds, like, how many signatures can you validate per second on the current hardware?
So we did a performance assessment, as you can see here. Some of the tests were performed on Raspberry Pis of different versions to see the uplift that we could have over the generations. Also with the latest Pi 5 to see if any hardware acceleration related to SHA-2 could be used for the Sphinx family of algorithm. On vehicle-grade hardware, as far as I recall, we didn't have the opportunity to test it, but we did test, in addition to here the signature key generation and verification operation, we did test network exchanges based on the size of different messages, so that we could have a look at latencies, etc. And the results are also available in SELFY deliverables on the website.
Okay, let's start again, the second part of this final event. So we will be first discussing about the validations of the tools that we have been seeing in the first part. We are also very happy to have a representative from the Connect project, which is a sister project of SELFY. He will be giving also a presentation. And then we will be having the discussion on upscaling of the results of these two projects, okay? So let's start by the validation. I would like to call on the stage Tina Volkers-Dolsver. I'm sorry about the pronunciation. She's working at THI as a security expert. She works to enhance the automotive security through attacks, adversary, security modeling, and threat analysis. As a volunteer firefighter, she's also applying the same urgency in this activity, in identifying, addressing security threats, and in connected vehicle environments. So, welcome, Tina.
Thank you. So, yeah, hi everyone and welcome. Let's start with the validation of the SELFY tools. So here's what we will cover today. Nice, okay. First, a quick overview of the validation, including the key aspects and activities. Afterwards, we will give some brief glimpse in the results of the validation in simulation, laboratory, and real-world validation, and into the Vienna experiment. Finally, we will conclude with the key achievements and a short Q&A. So let's start with a short overview. The main objective here in validation of the SELFY toolbox was the demonstration and the validation of the full SELFY toolbox in relevant cyber attack scenarios of the CCAM, the Cooperative Connected and Automated Mobility Ecosystem. And therefore, we focused on scenario-based testing and validation and an overall plan of the validation process. We considering continuous integration and also suitable validation tools, validation techniques. Yeah, and the SELFY project was divided into two iterations. The first iteration we focused on planning and defining the overall process for the validation, for simulation, laboratory, and real world, in relation to selected cyber attack scenarios. In this phase, each partner started with executing individual basic tests on tool level, but also first basic integration tests with small tool combinations. For example, the integration of only 2 tools. And we also started with simulation tests, for example, with synthetic data. The second iteration focused on the use case-based integration as the final validation step. Meaning, we executed tests across simulation, laboratory, and real-world environment. We continuously integrated the SELFY tools, including, for example, we had on-site workshops for the integration tests. And we constantly reported and assessed the results. So let's have a look and let's dive into the validation results. In the simulation validation, we focused on robust platooning within the CCAM environment. As you can see here in the ground, there's a simulated platooning of 3 vehicles. So next to the loss of localization capabilities, as for example Victor mentioned before, we considered in a use case the behavior-based attack and behavior-based attack. In this case, the attacked vehicle in the middle of the platoon pretends that it has successfully left the platoon, although it is still inside the platoon and even decelerates. And in this case, the SELFY tools collaborate, meaning the so-called IVT tool analyze the communication traces, and therefore the IVT tool needs the support from other tools, from other SELFY tools. It needs traces, communication traces of the vehicle sites. And in the picture on the right, that picture shows the setup. The right side laptop deployed with the simulation environment, and in the vehicle SELFY tools like the SOT tool and the robust tool. While the left side laptop evaluates the cloud-based SELFY tools with an instance of the VSOC and the IVT tool. In conclusion, the integration and the cooperation of these SELFY tools was successfully in simulation. We successfully detect anomalies in this kind of communication traces within the platoon. So let's switch to the other validation called, in this case, the laboratory validation. So in laboratory validation, we focused on secure backend systems of the CCAM ecosystem. On the left side, you can see the hardware and system deployment, so as well as roadside unit infrastructure, cloud, and also the vehicle. These are the tools, these are the deployment stuff that is involved. The flowchart on the right represents the use case story flow. Meaning, for example, this use case story flow represents that we consider different types of attacks for the backend systems. For example, imagine an attack forced in the vehicle, for example, by a malware. So we consider this kind of attack, as well as vulnerable software components and vulnerable update content. So the next slide, it is the related, you can see the related VSOC dashboard in this use case. The VSOC is connected to other SELFY tools and to coordinate, to collaborate within such an attack situation. The blue dotted line represents the connection. Imagine, due to an attack, and due to an attacked vehicle by malware, the artificial immune system detects suspicious behavior and informs the VSOC, that is represented in the red dotted line. With this information, the VSOC triggers the audit box as well as the remote attestation system service to get more details about the current attack situation. So in this case, the SELFY tools collaborate with each other to detect various parts of a complex attack. And as a response to the attack situation, the VSOC triggers the secure over-the-air software update tool. Finally, with a new software installation, the SELFY tools report no problems to the VSOC. As a conclusion, in this laboratory validation, the SELFY toolbox collaborate successfully with each other to detect various cyber attacks in this kind of domain for backend systems and trigger an update to improve the resilience for the CCAM environment. So I will hand over to Fanny because now I will have some other colleagues that will present you some more details about the other validation results in the real world.
Okay, thank you, Tina. Any question at this stage? If not, let's wait we have another Q&A session at the end of the validation. So I would call now Sergi Arjona. He's an automotive cybersecurity engineer at A+ IDIADA with a background of software engineering, embedded systems, and he's working to bridge the gap between innovation and regulations in the automotive security. The floor is yours.
Thank you, Fanny. So, as my colleague Tina was explaining, the validation of the SELFY toolbox was kind of divided in 3 stages. The first stage was the simulation validation. The second stage was the laboratory validation. And the third one, and kind of key and important, was the real-world validation. Why is this very important? Because this is the one that is closest to the real world and the reality. So in this occasion, we had the opportunity to test all the tools together in a real environment. To do so, all the SELFY project partners gathered together in IDIADA tracks, particularly on the urban area, where we could perform 6 use cases, 6 different scenarios involving different materials such as vehicle dummies, pedestrian dummies, cones, simulating intersections, roundabouts, etc. So I think that the best way to show you is we will go one by one for you see each use case, okay, and see the different scenarios that we could replicate. No. So the first use case was use case 18, which consisted of the detection of a vulnerable road user ahead. In this case, there is an attacker that tries to hack the test vehicle by sending a fake message. This fake message indicates the vehicle that there is an off-ramp maneuver available, but actually in the middle of the off-ramp, there is a vulnerable road user that the test vehicle is not aware of. So the test vehicle is kind of forced of using the perception of the roadside unit and the target vehicle, which they inform about this vulnerable road user in the middle of the trajectory. So finally, the test vehicle is able to detect that there is some mismatch between its own perception and the information that it's receiving from the other parties, and decides to finally abort this maneuver safely. The second use case consisted of the detection of a malfunctioning sensor. In this case, there is no vehicle because the attacker tries to hack the roadside unit which is supposed to detect a vulnerable road user using a LiDAR and camera, but the attacker hacks the roadside unit by occluding the camera perception. So the roadside unit identifies this as a misbehavior and would detect this as an anomaly and treat it. So the third use case was the identification of an unreliable CPM sender. CPM stands for Cooperative Perception Messages, which it's basically how different components in the scenario communicate between them. In this case, the test vehicle broadcasts a wrong CPM message, indicating that there is a vulnerable road user in the truck, which actually doesn't exist. He's not there. Then the roadside unit detects that there is a mismatch with what actually the roadside unit is seeing, so its perception, and would analyze the inconsistencies of this. And finally, the roadside unit would reveal that the test vehicle is wrong and would report this information to the VSOC. The fourth use case consisted about aborting an overtaking maneuver with a vulnerable road user too. This use case was, let's say, the most complex because of the number of parties involved. The test vehicle basically is overtaking the target vehicle, which represents a broken down vehicle with a possible driver next to the vehicle. So the attacker tries to hack the test vehicle location capabilities. So the car wouldn't be able to detect this target vehicle and would collide. But the test vehicle uses the roadside unit support again and the target vehicle support to enhance its perception. And then the roadside unit inform the test vehicle and that there is a VRU on the target vehicle on the road. And finally, the test vehicle would be able to abort the maneuver and safely stop. Another, let's say, variation of this use case is use case 44B, which basically is also an overtaking maneuver, but on this occasion, the hacker is not attacking the test vehicle. Instead, the attacker is attacking the roadside unit. So basically, in this case, is the test vehicle the one that would detect the mismatch of this information from the messages that is receiving from the target vehicle and the roadside unit, and again would abort this overtaking maneuver safely. And the last use case was use case 47, consisting of person and vehicle data anonymization with the tool that Adrian explained before. In this case, the attacker tries to access to the raw image of the camera of the test vehicle to obtain sensitive information such as the license plates or the faces of people. And the test vehicle uses artificial intelligence to block this unauthorized access and obfuscate this, let's say, blur this sensitive information. So these were the 6 use cases that we performed at IDIADA during the real-world validation, apart from the Vienna use case. And I think that the best way for you to see what really happened those days is through this video.
So SELFY project is reaching to the end, and today we are at the urban area of the IDIADA track with the vehicle of virtual vehicle, with the cybersecurity team of IDIADA and the rest of the partners of the SELFY consortium. During the project, we have developed a set of tools related to situational awareness, cooperative resilience, and trust and data management system. We have tested all the tools in simulation environments, laboratory environments, And today is the day that we will test the real-world validation use cases.
We were able to test the 6 use cases. We've been building different scenarios and maneuvers close to a real environment using dummies and also real vehicles parked. During the whole validation, we have been gathering all the data sets from all the tools involved in the validation.
Thanks for your attention. In case you have any question, I'll be happy to answer.
I have one question related to the use case 44. So you had 2 variations. One, the attacker attacked the ego vehicle, and the other one, the attacker performs an attack on the roadside unit. Is it possible to, as an attacker, to attack roadside unit and vehicle at the same time, maybe, to do not be able to detect the attack in the end?
Yes, it would be possible, but it would be actually a new use case. So I'm not sure about, I mean, yes, but it would be a different assumption for the scenario.
Because I think it might destroy whatever the vision of the project to some degree. You have on the one side the situation awareness of the vehicle, you have the collective perception, which is based on the overall detection of all the objects that are involved. And if that actor is clever enough to attack whatever, also the collective perception part, so then the validation would not work for the ego vehicle. So this might be incredible bad for the whole thing, right?
I think Christoph has some hints.
So maybe I'm from Virtual Vehicle, Christoph Pilz again. Maybe I can answer this a little bit. We have a basic premise with the vehicle, for example, that we say, okay, the vehicle has to be in control of everything itself all the time. So you have to have such basic premises. You, of course, can put a use case on top of it where you attack everything, but you have to be clear what is your ground rule. And this is one of our ground rules where we say, okay, the vehicle itself tries to be as aware of its surrounding as possible. And if there is something else, then, yeah, we see it as an attack.
May I also add something? Yeah. Just from the point of view of system of systems, I mean, this could be easily be scaled up to a distributed system when you have many agents, right? So the multi-agent system, you would increase robustness by increasing the scalability. So yeah, in this case, it is limited. I think it's just a use case scenario that was easy to implement for this project because of the scale and the budget that we have. But in terms of swarms or even like large multi-agent systems, I think this scenario will be reduced, but it's a very valid question.
Sure. Generate some debate.
Yeah, this is Mario from Tecnalia. So, as Christoph said, the cooperative perception enhances the awareness of the vehicle, but the vehicle is still capable of driving itself. So the same tool that in the use case of the platooning exited the damaged vehicle to the left to the right lane is still in charge of bringing the vehicle to the control stop. So even in the case of attack to the both sides, so the vehicle and the infrastructure, there wouldn't be any crash.
Are you happy with the answers? Thank you very much for this question. Thank you very much, Sergi, indeed. Let's continue with the other part of the validation, and I would like to call on the stage Gernot Lenz, who is coordinator of the traffic management in the city of Vienna. His background is on electronics, transport planning. He works in the fields of traffic management, traffic control, signaling systems, and CITS in Vienna. The floor is yours.
Hello. I will start with the real-world experiment in Vienna. Romain will continue afterwards. So, about CITS in Vienna. We started our deployment of CITS a few years ago because we want to update and improve the existing prioritization of public transport and at signalized intersections. We want to increase road safety and we want to optimize the traffic flow. Therefore, we participated in the C-Roads platform and in the project C-Roads Austria 2, co-funded by the European Union. We introduced 40 CITS roadside units. And as we see that this is a promising technology, we invested our own money and deployed 120 roadside units more. So up to now we have 160 roadside units out there in the city. So almost 15% of our signalized intersections are already equipped with a roadside unit, the CITS roadside unit. We implemented 13 use cases so far. The most promising for us is the SITLP, the signalized intersection traffic light prioritization we use for our public transport system. We use it for buses and we use it for trams. And in Vienna, we work with the ITS G5 standard, the Wi-Fi protocol 802.11p, for the communication between the roadside infrastructure and the onboard units within the vehicles. Yeah, and under our 116 unit crossings, we have to decide on one for the pilot site in Vienna, and we decided for the signalized intersection at Burgring-Burgtor on our Ringstrasse, which is around our historic city center. Why did we choose this one? There was already a roadside unit deployed, so we had to do just a few modifications. There was a camera on the roadside, but this camera doesn't meet our requirements, so we have to update it, replace it, but we can use the cabling which was there already. And we have there multiple lanes, multiple traffic modes. There are cars, there are cyclists, there are trams, there are buses. And on this 3-lane road, we have a significant traffic volume. So it was more likely to get also V2X messages from other cars than our own cars. We did a test drive over 1 hour with 3 cars controlled by ourselves, but we also collected messages from other cars passing by there. Yes, so this pilot site, that's what it looked like there. On the picture above, you can see the roadside unit mounted on a lamppost, because our department not only deals with traffic lights, we also deal with public lighting, so it's very convenient to use all this infrastructure we have out there. On the opposite side of the street, near the museums, there is this existing traffic camera. And in the middle, you can see the view of the camera on this 3-lane road, the Ringstrasse. And in this red circle, you see the City of Vienna car passing by with the CITS onboard unit. So, and now for the more technical things, I will hand over to Fanny and to Romain.
Sure. Thank you very much, Gernot. So, Romain, can you continue the explanation? So, Romain Belsorte is a R&D project leader at Canon Research Center in France. His background is related to image processing, AI, and he works on the infrastructure technologies in the CCAM. Go ahead.
Thank you, Fanny. Thank you, Gernot, for the introduction and explaining the context. So, as you've seen, there was some real-world validation in SELFY at IDIADA in controlled environment. But with the help of the city of Vienna, we could get access to real-world traffic data. And we thought it would be interesting to apply SELFY infrastructure tools to that real-world traffic data. So to do so, the data was captured by the city of Vienna in April. So it was some really real-world traffic. We did not control anything with real-world infrastructure, the camera, the RSU that Gernot showed. And so we obtained some video recording and V2X messages. That data was provided to us, Canon Research France, and we provided it to the two SELFY tools, the traffic monitoring tool, which converts the video data to list of objects with their real-world positions, with latitude and longitude. And that data, as well as V2X data, was provided to the threat evaluation tool, which compares the object identified in the video with the object described in the V2X messages to determine if there is a threat or not. The first outcome of this experiment is that we were able to validate the positioning accuracy. Indeed, we have two kinds of positions. The positions determined by the camera and the positions indicated in the V2X messages. So we need them to be accurate enough so that we can determine that one object perceived by the camera corresponds to one object described in V2X messages. So you can see here in a short video, on the left you have the real-world view, so traffic in Vienna with one vehicle that emits V2X messages comprising its own position. On the right, you can see the SELFY tools view. Many vehicles are detected by the camera, and one vehicle is also described in V2X messages. It's in green, because it is perceived by the two means of perceiving the environment. So that's a successful association. That's what we expect when everything works normally. Then the second outcome is that we were able to validate the threat detection. Indeed, since objects can be associated, you can analyze the consistency between the camera and the V2X to determine when there is an anomaly, and then check if it corresponds to a threat or not. So here we have the same video, but we simulate an attack by changing the settings of the camera. So you can see when we simulate the attack, the image is completely blurred. And so there is only one object that is indicated in red, because it is the object that is described in V2X messages, but it is no more perceived by the camera. And that's why it's in red, and that's why we see issue detected. Obviously, for this specific example, which is quite simple, image analysis may be sufficient to determine that there is a threat because the image is completely blurred. But in SELFY, we are more generic. We want to get generic solutions. And so when you rely on both the camera and V2X, you have two means of perceiving the reality. And so you can create a much more generic and robust solution to identify threats. To conclude, with the help of the city of Vienna, we were able to validate that SELFY infrastructure tools work as expected with real-world traffic data. And we consider this to be a very significant step in the validation of SELFY. Thank you.
Thanks, Romain. I will continue with the conclusion as an overall view for the validation of the SELFY toolbox. In conclusion, we successfully planned and tested the SELFY toolbox in a structured way at different tool levels, meaning on a basic tool level, basic integration tests, these small tool combinations, and also finally these use case-based integration tests as a final validation. The validation is related to relevant cyber attack scenarios of the CCAM domain, meaning we considered the safety of vulnerable road users, the secure backend systems, as well as the robust platooning. And these 3 overall scenarios are addressed by 12 use cases and 1 experiment, that one in Vienna. Regarding the associated validation environment, we successfully tested 2 cases in simulation validation, 4 use cases in laboratory validation, and the 6 use cases in the real-world validation, plus this experiment in Vienna. Finally, we documented the results in a centralized approach, including the recorded data sets that we recorded during the real-world validation. And that concludes our presentation. Thank you for your attention.
Thank you very much, Tina and team. Any question? We still have a bit of time for 1, 2 questions before we continue, related to the real-world validations. Online, do we have some questions? No?
No questions online.
Okay, so let's continue. Now I would like to call several people. Well, we have Victor, who is going to come here as the technical coordinator of the SELFY. But I would also like to invite Alexander Koenig. Alexander is working at Denso. He's the technical manager, Security R&D Europe. His research areas are the security, privacy, engineering, dynamic trustworthiness management, applied post-quantum cryptography, and he's representing the Connect project. As I said before, the Connect project is a sister project of the SELFY, which is funded under the same topic with similar activities, but still, I guess, some different points of view and different activities that enrich and complement the SELFY. So I would like first of all you to present the Connect, and then we will go for the discussion. Just before you start, I would also like to call Pau Vallès, who is an expert in exploitation activities at EUCAD. He helps us to to bridge the gap between the research and the market and the industry. So he will be there also discussing with us and supporting me in the moderating session. Okay, Alexander, go ahead, please.
Okay, so welcome everybody. Thank you for the opportunity to present an overview of our Connect project. And to do that, how is this working? Yes? No? Okay. I would like to present our project. I would like to start with our project slogan. And the slogan is never trust, always verify. At the beginning of the project, I was really struggling with this slogan, which we borrowed from the trusted computing community, because it's an achievable goal for systems you actually control. So, for example, in a data center, you manage on your own, you control the system, and it's achievable, still hard work, to verify the relevant security properties in the system. But for CCAM, things get a lot more interesting, because you need to cooperate with entities you do not control, and your applications, your CCAM services, need to make the decision whether to trust something you receive from an independent party to make a valuable service, actually mostly a safety critical service out of it. And for that, we decided to look into subjective logic, because trustworthiness is at the core root questions we wanted to answer. And we want to provide the tools for the CCAM services to decide whether to trust something in the CCAM ecosystem or not, to provide the service. And for this, for subjective logic, we span up like a triangle for decision making. So we decide whether to believe something, whether to disbelieve something, and also how much uncertainty is in this kind of decision. So for this decision making, we are collecting a lot of information in the system. So we start with the engineering process to find out which are the relevant aspects for our CCAM system. What do we actually control in our own, for example, car? What comes from the external part? We also include complex infrastructure. So we also include MAC systems, so mobile edge computing, but also further backend systems, infrastructure on the roadside. We are monitoring systems over the lifetime. So it's not like doing one trustworthiness assessment at the beginning when a vehicle is being introduced into the market or when the vehicle is being started, but we continuously monitor relevant properties of the system during runtime. Sometimes on a regular schedule, sometimes on demand if an application is entering like a critical situation and wants to be really sure if sensor data I'm receiving from the outside or if the sender itself or my own computation platform is trustworthy to handle this kind of situation. So for example, if you receive a conflicting data from the outside, you really want to know, be sure about the trustworthiness of the sending parties. Do I trust this car more than this roadside unit, or do I trust my internal sensors more than the external data? Because sometimes internal sensors also degrade or are under attack. And for this, we introduced a trust assessment framework or trust management framework, which enables the applications on the one side to specify what are the requirements regarding trustworthiness. So what is good enough? Because there is no 100% trustworthiness, as you know, because there is no 100% security. So this goes hand in hand. And also, our trust assessment framework is measuring what is going on in the field, in our own car, in other cars, is connecting all these things and is producing an assessment for the application. Then the application can decide what to do with it. Do I incorporate this data item? Do I need to apply some weights to merge some data? Or do I inform the user and do some responsive action like switching off the service? Or degrading the service, like, for example, introducing more safety space. One example here is we chose is CACC, Cooperative Adaptive Cruise Control. It's an extension of ACC, so keeping a safe distance from a car in front of you. And CACC also includes V2X messages. And one response would be to adjust, if you're not really sure about the situation, increase the distance to the vehicle in front of you. One really simple safety measure. So what we did in Connect is, so we also created like a hierarchy, a federated architecture, so because we want to be scalable. CCAM services can grow very large, the more entities you incorporate in your system. This also means that our assessment framework also needs to be scalable according to this line. So we federate our trust assessment activities, and also we decentralize from a single root of trust for CITS systems. So we consider there is no ground truth or ground entity that says something is trustworthy. It's very subjective, depending on who is asking and what is the question actually about. So Connect solves an open problem with this trust establishment in CCAM. So physical digital infrastructure for extending the operational design domain of automated vehicles plays a big role. Operational design domain means basically the situation a system is operating in and what the decision is actually about. If the situation changes, the ODD also changes. So we created trust models or trust assessment models depending on the specific ODDs. So for this, we need a mutual trust between different stakeholders, like an OEM, supply chain, external service providers. We need to support varying cooperation models of different types of data and feeds. This also goes not only which data do we consume, but also who do we share data with? Do we trust a receiving party to handle our data with care? For example, especially regarding privacy. Do we fully share something, or do we already obstruct certain information because we don't fully trust the receiving party? So Connect enables a dynamic trustworthy assessment framework for V2X messages. So we created a methodology and mechanisms to computate the actual trustworthiness at runtime, so assess the current situation, and also give a toolbox to application to specify what is enough trustworthiness for the operation, or also what is required to re-establish trust via responsive measures. So our methodology is currently heavily being discussed in pre-standardization. So we also discuss with ISO, but this is less technical, more high level, like at the methodology level. But we also discuss in the 5GA consortium about how to introduce this into the market. So to enable this, we also look very heavily into established automotive engineering standards, because it's the ground, the baseline for our methodology. So if we base our stuff just not on something established in the industry, it will be really hard for people in the industry to understand what we are doing and to make something out of this. And that's all from our side. Thank you very much.
Thank you very much, Alexander. Any questions to Alexander regarding the Connect project? If not, let's jump to the discussion. May I have the next slide, please? Okay, so after presenting the two projects that you have seen that we have some commonalities, we have some complementarities, these are RIAs, Research and Innovation Actions. The main question here is to know which would be the next steps and what should we focus on in the future to make it sure that the results of our projects are reaching the industry. This is what we are going to discuss. Next slide, please. Or maybe I can control it here, indeed. Yeah, so very quickly, we are going to discuss about important things such as, for instance, going to larger scale validations. Victor already mentioned this in some moment. We need more elements, more roadside units, more vehicles, more requests, and see how the system behaves in a real situation. We would also need, for sure, to have an audit layer, an additional audit layer at a general level to make sure that the SELFY, the Connect systems are working well too. But we also have quite a lot of important points related to standardization, to regulations. What about clear governances? Who should be owning the VSOC? Who is liable in case of a hacker entering into the system and things like that. And which is really important too is to keep user-oriented as much as possible, of course. And again, I will repeat this word, which is maybe the most important word of the two projects, trustworthiness. We need to make sure that at a large scale we can get this trustworthiness so that the CCAM systems are adopted by the society. Let's discuss on this. I would like Pau to support me in the discussion. We are going to give some work to everybody, not just those who are here. We have a Mentimeter, and we are going to raise two questions, mainly. The first one, I guess it is in the next, it's true that, you can go here. So we have a Mentimeter, so you can just take this code here, the QR code.
Exactly. You can use your phones, try to scan this code. If you want to participate, all your answers will be shown in the screen. So while Victor and Alexander are giving their opinion and the answer to these questions that we are planning to discuss today, you can also try to participate and give your opinion if you want to.
And this is also valid, of course, for the people online, that you can also participate. So let's go for the first question, which is really related to what I just explained. which would be the key technical enablers needed to scale up a project like SELFY, like Connect, across Europe? Who wants to start answering?
I think at the end, for a technical team or a team of engineers or whatever team, that they have to make some deployment of such a Connect project or SELFY project into the real world, let's say, no? Or a city that is interested to deploy such a system, or a government or whatever. I like the first answer that was here, which is clarity in the approach. So we need requirements. We need to know how the system has to be designed in order to be installed or to be maintained, or how interoperability, some standards on the messages that they have to be shared between all the tools. I mean, this it's also related to, before you said about governance and so on, liability and these concepts. I think nowadays is not so clear. And there are many actors like the OEMs, the red side units, the cloud, the services. But as a whole, we would need to have some clarity in the approach. I don't know who did this answer, but I really liked. I think for me, it's one of the most, for a team of designers, I think this would be really important.
So I would like to go in a very similar direction. So the biggest problem I see with CCAM is deployment. So we have established standards already for more than a decade for Wi-Fi-based CCAM communication, and up to now, only a few companies deploy this, and it will really benefit such research to have a pre-deployed field of CCAM-enabled vehicles or roadside units to actually start the work on a broader field. So at the moment, we already have some, let's call them silo CCAM services, so OEM-specific internal things, but this is no real cooperation. So the thing that's currently going on is vehicles report things to the backend, to the OEM cloud, and provide additional benefits to the single car. So yeah, broad deployment of established standards is one really big key enabler we need.
Any other comment from the audience? Because you are also participating. I would like maybe some of you online too. I don't know if we can hear you. I guess yes. So feel free, of course, to bring any other comment.
Yes, hello, I'm Alexander Jevtic. I'm from Ficosa, a tier 1 company. I was wondering, what is your opinion on how much regulation slows down? You mentioned standards, but in general, how much the strong regulation in Europe is slowing down the deployment of these technologies? For all, but mostly you. I know Victor already.
Okay, so regulation. So you can see it both ways. So for one, regulation can speed things up. The regulation can require implementing or deploying certain features. It's not happening yet. In terms of regulation slowing things down, I'm looking at safety. When I discuss CCAM services with my safety colleagues and discuss safety critical applications of these services, they start laughing, because they tell me this will not help them. So it's a nice feature, an added bonus, like an information basis for the driver. But if it really has a safety critical impact, this will never get certified. So they will never get it passed to the type approval regulation without having properly integrated this or an understanding of security or trustworthiness into safety processes. So on the one side, regulation can speed things up if they require things. On the other side, it's standing in the way if people are not able to integrate what they have into fulfilling regulations via using that technology.
I also see from the answers that you're just writing here on the screen that most of you have the same direction. Also, you say basically that the key technical enablers should be OEMs, road infrastructure providers, cities, governments, the technical infrastructure. But some of you wrote that there's missing a selling point, so monetization or additional benefit. Does anyone want to speak about this? No, now we are shy. Christoph.
So yeah, the selling point is from me. So I have to out myself in this project in general for V2X for being quite traditionally on automated driving approach, that the vehicle should do much of the work itself. The problem is sometimes, especially when I'm talking at home with my colleagues, they tell me, what are you doing with your communication? My vehicle does not need any communication with anyone else. It helps probably in managing traffic better, but in the end, there has to be a clear selling point that we want to have. I always work on those edge cases where you say, okay, you see people sooner, you can organize the traffic better and things like that. But in the end, there has to be a clear selling point that we cannot do without any other technology like that. That's where I'm coming from at the monetization. I just leave it here because probably it improves the discussion.
Maybe I would say that the topic is selling point monetization, but I think the automated vehicles, if there is not safety, we are not going to buy these vehicles and use these vehicles. So the OEMs need this technology, I think, but not only the OEMs, the society, because if we are a vulnerable road user and we are on a road and a vehicle runs over us because of cyber attack, or not cyber attack, also reliability or whatever, so safety, it makes a difference. If there is the safety, people are going to use the system. Otherwise, it's not going to be used. So monetization for me is, if you want this technology, you will need safety. So there is this safety security co-design that is needed at the end.
Any other comment, or should we go to the next question? Okay, so let's go to the next question. There is a comment. Oh, sorry, I didn't see you.
Yeah, it's a bit of a comment to Victor, actually. So you say, like, okay, for it to be selling, we need the safety, but for an OEM to be, it needs to be interesting. So the OEM, if they have an interesting selling point, then it's worth investing it for them to, in safety for themselves as well. So the question a bit is how much OEMs want to be involved in these things, because there in the end comes the money from, right? So if you have a selling point, then they will put money into it. It shouldn't be like European projects only, right? So I know what you...
Yeah, I mean, at the end, this is like kind of political discussion or whatever, but I would say that at the end, this technology has to come with regulations. I mean, some public regulation will say, I guess, I hope, that, okay, if the automated vehicles are on the street, they have to pass some regulations. And these regulations make that the vehicles are safe, and therefore they need security, but not only security, because safety is much more than security, but there is this co-design. So at the end, to answer that is, I think, it has to be mandated or an obligation. Otherwise, as you are commenting, OEMs, they want to sell vehicles and to gain the profit, the maximum profit. Yeah, this is.
Okay. Yeah, and one comment. So it was a little bit unfair to just put it, because I know already a few answers, because I had these discussions a lot. The idea is, so when I would propose something, what would be an interesting thing is, when we are going on the highway and we let automated vehicles drive there, we do platooning or similar things. Then we need the security in the background to guarantee that it is working. And this is the selling point. So you can say, okay, you're not allowed to drive, for example, in Austria or in Vienna with your automated vehicle if you don't fulfill this security part. If you fulfill it, then you're allowed to drive. And this is the benefit that the OEM can have, that they are allowed, for example, in Austria to drive if we open it. This is the direction I would go.
Indeed. Alexander, I think you wanted to add something.
Yes, so in automotive, we don't only have hard regulation, we also have somehow what I call soft regulation. So maybe some of you know NCAP or Euro NCAP. So Euro or NCAP is a rating system where experts rate vehicles regarding safety, so they give like rating in stars, and this is basically used for publicity. So you can advertise your car being more safe by having these NCAP stars. And what's currently being introduced over the next years is that to reach the full stars, you need to use connected services for safety systems. So it's not only hard regulation, but also soft regulation, that with these soft ratings, that it's being incentivized for OEMs to introduce CCAM systems. And maybe later, at some point in a distant year, these things could be mandated.
Thanks for all these ideas. It's food for thought, and especially for the dinner, because it's a long debate, I would guess. And indeed, we are going to the second question, because it was also about governance regulations again. So this is the second question I would like to raise to all of you, also through the Mentimeter. What governance frameworks and liability models are required to ensure the trust and the responsibility in the CCAM ecosystems? Some of the answers have been already given, but I would like maybe to go a bit more in depth within this governance and liability issue. Victor?
Yeah, maybe it's not only about the regulation in terms of security and so on, but also the RAMs is really important. So reliability, maintainability, interoperability. Imagine that there is one manufacturer installing the roadside units, and this manufacturer goes into bankruptcy, and then you need another manufacturer. If there are standards and regulations, you can replace. Otherwise, if there is not this interoperability, it's going to be difficult to replace it. So these other factors, maintainability, and you commented before, the audit the system, it has to be audited, and the liability you commented, if there is an accident, we have to audit who is liable, who is not liable, or where was the problem. I mean, there are many things that if we want these automated vehicles on the street, we have to advance a lot on these topics.
Just before you answer, I would invite all of you to give some answers here so that we can discuss.
Sorry, we know the governance and liability maybe is not as cool as the key technical enablers, but yes, please.
Alexander.
So I also need to confess I'm not a liability or governance guy. So this is a real hard topic for me. So you never achieve 100% security. That's forgiven, but somehow people need achieve getting certified for type approval. So this is the government's perspective. What we should consider is also certifying not like the optimal state we want to achieve at the end, but also different situations with security. How to certify how a system handles if something in the system is not on par as expected. And with CCAM services, these very complex and diverse systems, we need to prepare for having different kind of situations certifiable, and not only go for the full goal, which will in the end will be really hard to achieve, but also going in smaller steps and having different situations handled.
Any other comment? I see interesting things here in the screen, indeed. I see that different trust scores for different CCAM entities. This is a good idea. Data privacy, again, of course, this is a must. Insurance companies, this is really important to my opinion, because at the end, the insurance companies will also have a say when defining the liabilities and the penalties and so. So this is an important debate, also considering them in the discussion. I don't know, Pau, if you want to raise any other...
Yeah, no, maybe just give the word to any of you who wants to collaborate. If you want to develop more your answers, as the ones that Fanny mentioned, for example.
Maybe I wanted you, Mar, about that, but I know because there are some people that they also say that maybe too much regulations could hinder the system, no? And I think you have something to say here, because you are representative that maybe it happens also to the engineer team that we have many standards and you don't know which standard to follow. Maybe with the regulations, if they are too much, I know a bit your point of view, so.
Yeah, Mar Folgeral from THI speaking. Our main expertise is safety in the automobile sector. I come from the OM point of view. I have worked for years in the OM in the vehicle safety as well. And I'm definitely not an expert in regulations, but what they observe is that in Europe, we have an issue with regulations because it's very important, definitely. Without regulations, we cannot follow the things. But in some point, we need to stop and to decide we want to deploy something, or we need to dedicate us to a very, very incredible expertise in regulations. Because at the end, we live in a global world, and there are other parts of the world that has followed other rules. I think that we don't need to copy the rules of the others. We have our own criterion, and we need to follow with this. But we cannot avoid we need to be competitive. And then in some point, we need to analyze why we are losing in some way the competitiveness in compared with others, and then to reach a balance in this. Because if we don't deploy the technologies that we have, if we don't deploy the CCAM vehicles, if we don't deploy this, we cannot learn. And at the end, we need to buy these technologies that other parts of the world are developing and deploying. So, and then I think that Europe is complex, is clear. We are proud about our discussions and different opinions and respect of everything, but in this point, the regulations, I think that it's playing a bad role and in this deployment. That I think that everybody agree that if we have technologies and it's the next point, it's the next step. And the regulations in concrete perhaps stops the idea or the decisions of the people who have the technology can deploy this. Yeah, this was what we have talked at the beginning, and yeah, this is a little bit a summary.
Maybe regulations, yes, but agile regulations, agile and fast regulations.
Exactly, and try to simplify, also to reach the level that are really important and the complications, that everybody want to say something, and regulations in one level and another level, and regulations in one country and the other country, and then in a local way. And so at the end, should be easier. If not, we cannot deploy at the end of the day any technology or any vehicle on the road. And of course, at the end, we can not be competitive in this sector. Yeah.
Thank you very much, Mar, for this interesting input. I think this is also giving us some hints to be discussed during the dinner, indeed. If nobody else has any comment, I don't know if you want to add some questions from the table side. Alexander, do you want to conclude something? Victor? Okay, from my side, I've written here, again, the large-scale deployment, which involves quite a lot of activities, such as more elements, more requests, and so. Trustworthy. I think trustworthiness is one of the key words here in order to make the society adopt the CCAM. Regulations and governance, but also competitiveness. I like this conclusion because it's true that it is opening quite a nice debate among ourselves that we should also consider in next projects as a follow-up of the SELFY of the Connect project. So I like these ideas quite a lot, and we can discuss them further. If we have no more questions, we are coming to an end. So I hope you enjoyed the session. I would like first to thank all the speakers that have been explaining the two projects here. Thank you very much to the speakers. Also to the SELFY part. I would also give a special thanks to the full SELFY team for all the work done during these 3 years with very, very nice results indeed. So thank you very much, the SELFY team. A big thanks to the audience here, but also online. We know that we have quite a lot of people online too. So thank you very much to all of you and to your participation. And finally, many thanks also to the CCAM partnership. I see Marzena there, over there, and also to the European Commission, who has been supporting us during the full project, and that I am pretty sure that they will continue supporting us in this exercise of upscaling the SELFY Connect results in the future. Thank you very much. Don't hesitate to come to us for any questions that you may have. And also, if you are interested in participating in the follow-up of these projects, if you have new ideas on how we should upscale all this work, we could build some interactions and some collaborations together. So I would invite you all to come to us, to discuss with us, and to set some collaborations in the future.